Good evening, everyone. I hope I didn't bite off more than I can chew at this talk because I was looking for some, maybe not rhyme, but a little bit of smooth sailing on the title. And so the myth, methods, and models, we're going to give it a try, and we'll see how it goes. Okay, so this is a talk where I'm trying to sort of lay the context of how people thought about the water cycle through time, how their methods were informed by their conceptualization of the problem, and then how the models have evolved. And there's been a whole evolution of scientific models that are very much related, that even cross into the population biology and other areas. So I'll start off with reviewing historical concepts of the water cycle and with the idea of answering questions of where does the water come from, how long does it take, and how do we measure things like age and residence time. I'll talk about environmental tracers and their signatures in developing a tracer in the water cycle, and give an example of stable isotopes in precipitation runoff in a critical zone observatory that I was a PI on for several years. Then I'm going to talk finally about a new model for dynamic tracer age in the water cycle that we're hoping that will have a lot of applications to better understanding our environment without having to do new parameterizations, let's say, or understanding or getting a lot more field data. And I'll talk a little bit more about what I mean in that regard shortly. And then finally, I'll just wrap up with some implications of why knowing the age of water is an important idea, because it's a measure of how we might look at accelerating and decelerating climate change impacts. Agriculture, the time it takes for agricultural contamination or industrial contamination to move through the system. The effects on the hydrologic cycle of things like reservoirs and agricultural drains. And then finally, I think there will be some important implications of this idea for the carbon cycle problem. Okay, so we've all seen a picture like this. And this is the U.S. Geological Surveys, and maybe it's actually many people's rendition of all the processes that are going on in the cycle. And so it's sort of what we know in a nutshell about the hydrologic cycle, you might say. On a more quantitative level, we might look at a water budget or balance where we actually use models to partition. What is the vegetation water use in the canopy? Things like interception. Canopies intercept water, and they use, in this particular case, a pretty large fraction of the annual water budget. 100% is precipitation. And then we have runoff, groundwater recharge, infiltration, base flow to rivers, and all of the components. That's why we need models, is to sort of partition the relative importance of these components. Okay, so how do we know what we know, and when did we know it? And I thought I'd go back to some old documents that I used to collect these monographs when you could afford them, but now they're too expensive. This is Herbenius' treatise in Latin called Cataractus. And so this is the frontispiece. And so you have Neptune here putting oil into the sea monster. They're talking about the Mediterranean and the Nile. And you have the wonderful cataracts from below the sea consigned to the abyss, and the cataracts from the world above the land that returns to the sea. It turns out that an English professor, a friend of mine, brought this into coffee one day, and he says, "I bet you know what this means." And I says, "Yes, it's the reverse hydrologic cycle." And so the reverse hydrologic cycle was also represented in this picture by Kierkegaard, about 1670, and I think you can sort of see it. In the Mediterranean, we have whirlpools. That was his sort of idea about how water got back to under the mountains, and then there's two parts to the hydrologic cycle. The forward one, where you have rainfall, infiltration, and runoff, and form springs at the head of these streams. And that's the white lines here. And this is, again, probably the Nile. And then the dark lines are the subterranean one. They never, for 2,000 years, they never felt that rainfall was sufficient to make rivers. And this is the idea of the hydrologic cycle right up to almost the 1900s. So it's sort of remarkable that it's lasted so long. So the reverse hydrologic cycle said, okay, we know there's precipitation and there is runoff in rivers, but we don't think it's enough. And so this idea, it actually goes back to very early BC in the Greeks, that the sea, because it's so always the same level more or less, would have waters that would go back, and the heat of the earth or some other mechanism would bring the water back up to springs, and then that would be sufficient to sustain rivers like the Nile or the Danube or other rivers. The forward cycle is a standard one. Again, we have evaporation over the oceans, come over the land, precipitates on the land, and then we have some infiltration and river flow. Okay, so it's actually a combination of those at this time. And this is James Dooge, a very well-known hydrologist, Irish hydrologist, who made this quote: for over 2,000 years, the dominant theory of the water cycle was that somehow the interior of the earth, water from the interior of the earth was lifted by some mechanism within the mountains and emerged as springs to feed stream flow. And so the sort of full theory after Dooge's paper on this starts with Plato and Aristotle in about 390 BC. They said, yes, there must be a reverse component to the hydrologic cycle, but they also understood the forward part of it. So it's not to say that, so this was their idea. William Caxton in Mirror of the World in 1481, probably the first encyclopedia, also voiced this opinion. Leonardo had the idea of reverse hydrologic cycle as well. Bernard Palissy objected. Bernard Palissy was a ceramicist, and he was one of the first that voiced and wrote a book on it, part of a book, where he pointed out that he did not feel that the reverse hydrologic cycle had any merit. Kierkegaard, we just looked at his, and Herbenius, both of those posed the reverse hydrologic problem. The very first water balance that refuted the theory or suggested that rainfall was sufficient to form rivers was Pierre Perrault, and then there was Edmé Marriott, who confirmed this in the late 17th century. Edmund Halley, however, a very famous physicist and mathematician, supported the concept, and he wrote papers on evaporation from the Mediterranean and gave some very nice ideas about how that worked, but he was still, in 1691, convinced that the reverse hydrologic cycle had to be important. I think it's probably safe to say, at least according to Jim Dooge, that John Dalton did the very first complete water budget, almost complete water budget, for England and Wales in around 1799 in the Manchester Philosophical Transactions. And so that's sort of a nutshell view of the history of this idea of the reverse hydrologic cycle. Okay, so with that as background, because if you're going to do age of water, you have to have your concept about where the water's coming from first. And so I spent a little time doing that. But here's how the more modern view might calculate things. And you can see these are layered aquifers of confining beds and permeable beds. And the flow paths are distinguished here. And they're also sort of chronologically labeled as the time scale here is days to years, then centuries and millennia as you go down to, hundreds of meters to kilometers. And so this would be how we think of it today. This is very much what you might call, as an engineer, would call a kinematic idea in that one could calculate hydrologic time just by knowing the velocity field. Just by having a map of the flow field, you would have the ability to calculate time. And it would look something like this as a kinematic age. Just follow a path, you know its velocity, and then you can integrate along that path with respect to the velocity the travel time, tau. So that's a very standard practice. That's one way to get the age, and that's just what they're doing in this graph. Well, there's another way to get it, and that is think about particles, where you might look at the relative age of tracer particles in the water cycle, and we'll have some volume here. Maybe that's your catchment, your watershed. And the way that's done is we look at the distribution of age of the particles, the amount of time that a particle spends in a volume. And so you have some shape of that distribution. You have some moments. Here's the mean. You have the variance, would be the spread. And E is what I'm calling the distribution of those particles relative to a tracer or a chemical or other, you could even use temperature in some sense. Okay, so the problem with this is we need to know what that distribution is, and we almost never know it, which is the dilemma. This idea has been widely used in chemical engineering and batch process. It's been widely used in hydrology as well, by making the assumption that I know what the distribution is. Okay, so a couple quick definitions. The residence time is the elapsed time for a dissolved particle to travel from the input to the output or exit the system. Age is the elapsed time since a dissolved particle entered the system. And so the age is sort of a statistic of what's in the system, and the residence time is what's leaving. Okay, well, a little bit of distribution theory, and so you could say the residence time or exit time distribution it's a probability density, so it has to sum up to 1. Its fraction of particles that leave with age less than tau is just the integral up to T1. The fraction of fluid that leaves with age greater than is the complement to that 1 minus. And the statistic again is the mean age of the system is the first moment, or the sum of T times the distribution. For an exponential distribution, T bar here, or tau, is just the volume of the system over the flow through the system for a steady state flow. So that's another way we can get the turnover time or this residence time idea in an arbitrary reservoir, is just know what the volume is and know how the water is replaced or displaced. Okay, so there's different kinds of these residence times. This is the exponential one. This is a very commonly used one in many areas, and this is a paper on the atmosphere. This model was used in the atmosphere by Bolin, Rode, and Tellis back in 1973, and they wrote a beautiful paper on using residence time calculations to look at how tracers, contaminants, were turned over in the atmosphere. Another kind of residence time is the Gaussian one, normally distributed residence time. And that has a different characteristic. And matter of fact, if we look at an arbitrary reservoir, say a geophysical reservoir of some kind, a watershed or an aquifer, if you have an isolated source and an isolated sink, you tend to get a Gaussian type distribution. And if you have a distributed source and an isolated sink, you tend to get the exponential. Qualitatively, that's what happens. And so that's also how you might define a point and a non-point source. So this could be a river with an upstream input, and this would be the downstream, where this would be a watershed where maybe an agricultural contaminant is contaminating the whole thing, and it leaves in a river. That would be the way to think about it. So they're sort of end members. The average residence time for components of the water cycle, they vary a lot, but you can get some ideas here. Oceans, 3,200 years. Lakes, 50 to 100 years. That may be a little long. Atmosphere, 9 days. So things turn over very quickly in the atmosphere, where the shallow and deep groundwater, for example, less than a year, up to 200 in the shallow, up to 10,000 in the deep, or even longer. Okay, just to give you some ideas. Well, I wanted to also look at the roots of where this may have come from, or some of this idea came from, and it's population biology. So very early on, people wanted to know how do populations grow, and the model is just the rate of change of the number of people in a country or in a continent. The births, this is the birth rate times the number, minus the deaths times the number, and this would be the very simplest kind of model. It has an analytic solution that's exponential, so the exponential growth idea. However, this model only keeps track of the overall population. It doesn't tell you anything about the details or the structure of the population. What about the males and females? What about the different ages, age distribution? So we would like the model to have some structure with regard to the people or the particles in our case. And so this is what we want to try to do. And I thought I'd put in just a few plots from the web on age and gender, and these are called butterfly plots. So you have the males on this side. It looks very exponential. And the females on this side, and this is their relative ages. Lots of young people in Afghanistan. But when you look in, where's this? Oh, that's the US. That's not really Gaussian, I would say. It's almost uniform in this range, and then it tapers off here. And here we are in Italy, where the very young, there's not so many. And so the idea is that structure is quite important to understand, and it's going to be quite important for tracers in our environment as well. Okay, so the second part of the talk has to do with environmental tracers, sort of the methods and the experiments that we use to capture this age idea. Okay, and I introduced another term that you may or may not have heard of. The ecologists have coined this term called the Isoscape, which is a terminology to understand how isotopes, stable isotopes that are carried with rainwater, what their patterns in space and time are. So it was coined by, Bowen talks about this, and I'm not just sure who it was, but his paper talks about when it sort of started. As part of my work, we were developing a new theory for interpreting isotopic age and carbon in catchment systems, and I hope to be able to demonstrate the concept with an empirical model for isotopic patterns over the catchment. This is some work by Kendall et al. On the patterns of isotopes plus landscape equal isoscapes, and this is the pattern of precipitation for oxygen 18. So oxygen 18 and hydrogen are two isotopes of water. And you can see that this is what the oxygen 18 looks like in rivers. So there's a signature here that is a function of longitude and latitude, distance from the ocean. It's a function of temperature, and so the isotopes are really governed by their environment, and the seawater becomes the main source, going back to our water cycle idea. Okay, so with that kind of an idea, you can see that we might want to be able to use these to understand where the water came from and where it's going. Well, I'll mention very quickly one more idea that's very new. Kei Yoshimura, he's a atmospheric modeler from the University of Tokyo, has been working to simulate isotopes, stable isotopes in climate models. And here's a 10-kilometer resolution mapping of the oxygen 18 deuterium for a few days. I can't quite read it there. It's January 2011. And this is the patterns you get. And then there's also isotopes in the, I think that's in the vapor, water vapor, and this one is in the total precipitable water. So you get different patterns and these are now simulated. So we don't even necessarily have to have tremendous amount of rainfall documentation and experimentation that is quite expensive to do in the case of stable isotopes. I'll just turn this on to give you a sense of the time evolution, if I can get my thing under control here. There we go. And so this is what it looks like for what we call the reanalysis period. It's a 30-year history of a reconstruction of the oxygen 18 over the Northeast on a 10-kilometer grid. And so the patterns you see are related to terrain and temperature and weather, and they become inputs to the catchment that then we can begin to use to create these signatures. Okay, you got the idea. It's pretty variable, but there's a very strong seasonality, it turns out. Matter of fact, we tested that seasonality at our CZO, our Critical Zone Observatory in Pennsylvania, and the blue lines are our experimental data, and the dark line here is the mean, and the variability of the model from Yoshimura is also shown there. So it doesn't do too bad. There's some departures, but it captures sort of the seasonality reasonably well, and this is the whole record, 30 years of daily data that we can bring to bear on a lot of good hydrologic problems. Okay, so this is our Susquehanna Shale Hills Critical Zone Observatory. I'll quickly give you a little background on it. We have the Rose Hill Shale underlies this site, very thin soils. This is a wintertime image, and it's totally covered by forest, deciduous forest with a few coniferous trees in the valley. Many of us have been working for several years to monitor all components of the isotopic signal in the watershed with lysimeters. Sue Brantley led that charge, installing those. I led the drilling of the groundwater wells, the blue, and then we had an eddy flux and a climate station up here with many, many more samples. We had automated sampling of rainfall, so this is a gold sensor that tells it when it's raining. It's a German product, a very nice piece of work, and then it'll collect, every 6 hours, we'll collect an integrated sample of water that we take to the laboratory. We have wells and stream samplers, automated lysimeters, and we do our isotopes with a laser instead of a mass spec, and it seemed to work pretty well. Okay, so here's the results for almost 4.5 years of study, where on this axis it's deuterium, and on this axis it's oxygen 18. There's the sampling plan again. And these are rainfall, is the blue, orange is soil moisture, green is groundwater, red is stream water. So we tried, and as a matter of fact, I'll also point out the yellow here, that is tree water. So we sampled the water of the trees as they were transpiring to try to get a really complete picture of the story. We look at the composite for oxygen 18 and deuterium over the soil profile. This is a 3-meter depth. This is the kinds of variability, and that's a simple model. So you can see the data fits. Well, I mean, it gives you this idea that the isotopes look like a temperature profile, in fact, and they do. So the seasonal cycle attenuates greatly over the depth. The groundwater starts to be saturated about this level on the average. Okay, so now I'm going to talk about how you can take this data and turn it into a mapping empirically that can lead to age modeling. Okay, so this is the Isoscape idea. And so here's our watershed, and this is the elevation contours for Shale Hills, and this is the aspect. And so this is a northeast, northwest, this would be northwest, the blue here, and then this is south facing on that side. And so what I want to do is build a sort of empirical model of the isotope ratio as a function of elevation, aspect, and then it's a polynomial here for the steady state or mean value, and then have a time-dependent value for the soil profile, because what you can see back here is this is the range of precipitation, but as I go down in the soil, it attenuates. And so what we want to do is capture both of that, and so we'll get some cosine terms here to do that. All right, so here's the mean field for oxygen 18 for Shale Hills. When you do that regression with the data we had for lysimeters, groundwater streams, etc., we get a very nice pattern with somewhat more negative on the north-facing side than on the south-facing side in general, with a very strong negative patch here. And so there is an asymmetry in how trees probably use water, and so we have that impact. We haven't really determined all the implications of this yet, but because this is pretty new. Okay, so that's the Isoscape that we've built, and now what we want to do is see if we can get a preliminary model of the age of water in that same catchment. And so the idea here will extend to things like lakes and reservoirs. It'll also work with the soils. And so I have to tell you a little bit more about this model, because I want to capture more than just the number of particles that are out there, the population idea. I want to capture some of the structure of age. And so think of it like this, that at a point in my watershed, there's some tracer or isotope going in with the rainfall, and at different times it takes slightly different paths or maybe very different paths to some observation location. And that distribution C is a function of time, but it's also a function of the age, the time it takes for a particle to move along a path and get to that. So there's a time and age idea here. As a matter of fact, we assume that there's a joint distribution of this concentration as a function of time and tau. And you might say it looks something like this. I stole this from geophysics distribution of earthquakes because I didn't have a good joint distribution that looked this nice. So it's a Mathematica document. But the idea is that here's your probability, here's the density, and here's time, and here's tau. So particles depend on time and tau. Okay, so if we know the distribution, we can go back to what we said about that E function early on and just calculate the moments. So we can get E to the mean. The 0 orderth would be the mass. The first moment would be the mean, etc. Here's the 0th moment. That's the concentration. I integrate over tau here, so I get the concentration. I integrate again with respect to tau, and I get the first moment. And it turns out, by definition, the ratio of those two is the mean age of water. And that's the whole hook of this model. And it was initially proposed by some oceanographers, and we've been using this idea. This idea is not new. I'm not trying to say that. But I will say that you'll see in a moment that there's some implications for catchments that are unique. Okay, so what it means is that our model needs two terms. The time rate of change of mass in the system, here's my volume, depends on time and tau. And if I work with the concentration, I got to solve this thing. And that's what population biologists did. So what the ocean guys did is, no, what we're going to do is integrate that equation over tau. And when you integrate over tau, you get a more simple form of the equation. Here I start and I integrate this over tau. I get moment equations for the 0, 1st, 2nd, 3rd. And there's the sources and sinks. There's the coupling term, n-1. So the 0th moment affects the first moment. And that's source terms for the nth moment. Okay, so let's look at a simple system and see what we can do, because this actually opens the door to do time dynamic systems as well, where most of the population biology is, or the analogy to population biology or residence time idea is steady state. So here's my catchment. Let the volume in the system, water volume in the system change in time. Here's my input, output. Here's the concentration equation. Here's the first moment equation. And notice there are no new parameters here. I just solve this one and I can immediately solve for this one because the input, output from this is input to this, and then take their ratio and I get the age for nothing, or a little bit of computation. So that's the whole idea really of this new approach. And so let's get some ideas. If I have a 0 initial condition and I have a unit input for the flow, it goes to steady state at some time. The concentration has a little longer time constant, but for a unit input, it also goes to steady state. But the age goes up, and notice where it goes. At a long time, it goes to volume over flow, which is the way we define the turnover time in the first place. So up to that point, it's a transient. Age is a transient phenomenon. So imagine the particles on the average are changing in time if you have a dynamic input. So finite age at large time is the other issue. Okay, so here's an interesting thing that I didn't realize is that do that same experiment, but then turn off the hydrology. No more rain, we're in a drought. When you turn off the hydrology, what happens? This is an analytic solution, it turns out. The hydrology goes up by a clock. It becomes a clock. So basically, if you don't have active hydrology, like what's happening during a drought, what you end up with is a simple clock, and the age just gets old. Everything just gets old in clock time. So then if you look at random inputs for flow, that's the red, and random inputs for concentration, that's the black, the age is all over the place. So this idea that age is a slowly varying process in these systems is probably not a good bet. It depends on the hydrology. It may also depend on the purpose that you have in mind, because the mean of this is the steady state age, the volume divided by Q of the mean values. So in general, the age of tracer accelerates or slows down depending on the system flow dynamics and the source of tracer. So given that kind of background, I'm going to skip over this other one. This is just a more complicated case where we have macropores and fast flow and slow flow in a soil, for example. And the immobile part of the water gets older than the mobile part of the water. And that's a useful model, but it doesn't add anything to what we did already. In this case, we get two distributions that don't look Gaussian and they don't look exponential. So the real thing seems to be nature doesn't conform to any of the kind of classical functions for most cases. Okay, so what we've done more recently is generalize this to a spatially and temporally distributed catchment. This is our Penn State model. And so what we're going to do here is try to estimate the age in a domain with spatial structure as well as time and age structure. And so we would like to know, how does that system evolve in time given a dynamical input for rainfall, evaporation, plant growth and water use, hydrogeology, etc. And so Gopal Bhatt did his PhD on this, and this is just extending it to a lake model. I'll skip that. So here's a simple result. Well, not so simple, actually. You get this is a homogeneous soil assumed in the model. The only thing that's different is the slope. So the rainfall is uniform, the temperature and radiation is uniform, but what happens is you get these patches because the older is the redder and the bluer is the younger, and so what emerges is local water budgets where there's more evaporation or more recharge. That changes the pace of the hydrologic cycle, it changes the age. And I always thought this was an interesting experiment to see all this spatial variability with almost homogeneous inputs. Now, the average age is 217 days. That's how long it takes to turn over that water, and that would be the age of the water leaving, relative to the isotopes now. There's the distribution, and I could talk quite a bit about this, but I'll skip over it. It turns out this is the residence time, meaning that's the age of the water that's leaving the watershed, and at small time you see a lot of parts of the histogram that are not zero, and what that is due to is thunderstorms at the end of the summer. Okay, so punchline. This is a 32-year simulation of the residence time. This is the rainfall here. You see the seasonality in the gray in the background. That's the seasonal variation in age. And then this is the annual mean. And you'll notice it has a trend. The hydrologic cycle is decelerating in this watershed, we think, due to climate effects. And so basically, the rather small increase in temperature is actually causing the thing to slow down, like the drought example I gave. And so it's getting older on the average. And so this is the kind of thing I think we're going to be able to use in the future in a very serious way to begin to look at impacts of the hydrologic cycle and how we can simulate age to give us some more guidance on detecting change. So the implications of knowing the age of water: acceleration, deceleration of environmental cycles, residence time of agricultural, industrial contaminants, reservoir impoundments change entirely the age structure of a catchment. What happens when you put a big dam on these large rivers is you are affecting the water quality, you're affecting the flow, but you're also affecting the store of water for good or bad. Obviously, for flood control, that's important. For other things, it might, ecosystem services, it might not be so good. And of course, for carbon sequestration. And in sort of conclusions, I think the Isoscape age model is a new tool that is a modest increase in computation with no new parameters. It does require that we either have there are a few more parameters. We need to know the transport parameters, the dispersion coefficients and things, but usually they're not too bad to get. The Catchment Isoscape provides a way to map environmental tracers and uncertainty in time and space, potentially. And the catchment age model has important implications, as I mentioned, for things like the residence time patterns for salinization. What's happening when in arid zones when the water becomes salinized? We're taking water out, we're slowing the hydrology down, potentially. Irrigation would speed it up. But so partly there's some important signals we could be looking at. Fertilizers, pesticides would also be another thing that could change the residence time. Atmospheric chemicals and tracers, reservoirs, as I mentioned, and climate change intensification would be another. One of the problems we've begun to look at is glacial retreat, such as in Switzerland, and where glaciers have been receding since the 1850s. And that's accelerating the hydrologic cycle as it's decelerating the glacial cycles, I guess you'd say. Okay, well, I think that's my talk. I thank you very much for your attention, and I'm very happy to take any questions.